So we usually, when we start talking about integration or an integral, what we do is we talk about it in the context of finding area under a curve. So for example, we might start off with a problem like this and we say, okay, I want to consider this function f of x equals x squared on the interval 0 to 1. And what I want to do is I want to calculate the area under that curve. So maybe here's 0 to 1. I want to get all of this area right here. Okay? This is usually where we start because it helps us to understand what an integral does. Now, the way we approach that is, since I don't know of any formula to calculate, this isn't like a square or something, or a triangle where I have 1/2 base times height. This is a curvy thing. So usually what I do, or what we do, is we say, well, from 0 to 1, let me do this. Let me divide this thing up into components that I can find the area, like rectangles. In other words, I might want to divide this thing up into just a couple of rectangles. And I know how to find the area of those rectangles. Notice that if I divide this thing up evenly, if this goes from 0 to 1, this would be 1/2 right here, right? So I could say, okay, I'm going to approximate the area under this curve by saying this is 1/2 the width times the height, which is f of 1/2, plus the width here, which is 1/2 as well. See, I'm getting this rectangle, and f of 1. And I could say, oh, okay, that's an approximate area under this curve. But it's kind of sloppy, right? You notice that I've got too much left over. Like these rectangles, yeah, I can find the area of a rectangle, but that's not really a good estimate of the area under the curve. So I search for ways to improve my estimate. And notice here I use 2 rectangles, so let's call that n equals 2. And the width of each rectangle I'll call delta x. Delta x was 1/2. See, on both cases we had delta x was 1/2. Now, maybe I want to be more accurate in getting the area under that curve. That's what I want to do. So one logical approach would be to cut down the amount of error I have here. Look at all that error. That's way too much. That's an embarrassingly large amount of error in my estimate. So I might go back and I say, okay, let me make this to have 6 rectangles instead of just 2. Now, if I have 6 rectangles, let's see, that means that delta x, I'm going to divide that interval from 0 to 1 by 6 equal, into 6 equal parts. So the delta x is 1/6. So now I have skinnier rectangles. Okay, so let's see what that might look like. Let's just take a gander here. Let me draw it. Okay. So look what I'm going to do now. I start here at 0 and I add a delta x to it. That's going to be 1/6. And then I add another delta x. See what I did there? 1/6, there's 2/6, and then I add another one. And then another one. See, I'm just adding these things. And now another one. And I keep going until I get all the way over here to where I have 6 rectangles. Now notice, I'm here at the end, and I have 1/6 times 6, right? And that's 1. So see, I'm going from 0 to 1. Now if you look at this, let me make the curve up here. You can see what I have here. I have the one rectangle here, another one. So I'm kind of constructing these rectangles so you can see what's going on. Okay, so here's my first rectangle. Here's the second. And there's my rectangles. Let's see here. 1, 2, 3, 4, 5, 6. Yeah, 6 rectangles. Now, I'm going to have, see, it's not like I have two rectangles and have all that extra area up there. And I kind of blew this up just so that we could see what's going on. But notice what we're going to do here. I'm going to add up all these rectangles. And notice the way I'm going to do it. I'm going to take 1/6 f of 6. That's this first rectangle right here. See how the width is 1/6 and it's f of 1/6. Now dig what I'm going to do now. I'm going to take 1/6 f of 1/6 times 2 for the second rectangle. See? And then I go 1/6 f of 1/6 times 3. See, that's the next rectangle. See, I'm just adding up all these areas. And I keep going with this. Okay? And then I've got 1/6 f of 1/6 times 5. And then finally 1/6 f of 1/6 times 6. Does everybody see what I did? So notice, I added the first rectangle, the second rectangle, the third rectangle, fourth, fifth, sixth. There's 6 rectangles here. Now, if I add this up, what I'm going to do is I'm going to get an estimate of the area under that curve. I'm going to add up all these rectangles. I added 6 of them. Now, let me ask you a question now. What if, instead of 6 rectangles, what would change if instead of 6 rectangles, I had n rectangles? I just had n. Well, instead of 1/6, this would be 1/n. Okay? So I would have 1/n. And this would be f of, this should be 1/6 here. It looks like I put f of 6. It's 1/6. So then this would be f of 1/n. See? See how this would change? And then I would have 1/n, f of 1/n times 2. See? Here's f of 1/n times 1, f of 1/n times 2. Then I would have 1/n, f of 1/n times 3. See? I'm just replacing the 6 with a n. Now, plus, I don't know how many rectangles. I know there are n of them. So I go all the way to the end. My very last rectangle is not 1/6 f of 1/6 times 6. It's 1/n f of 1/n times n. That's my last rectangle. Okay? So I'm just generalizing. I'm just setting this up. Now, look what I can do now. I want to represent this with summation notation. Okay? So look, let me see if I can write this. I've got the summation 1/n, okay, f of 1/n to the times, let me put a k in there. And k is going to go from 1 to n. See that? See? So dig this now. Notice if n is 6, like it was up here. Let's see what happens. If n is 6, we put in a 1. We got a 6 here. Okay? So if n is 6, here's what we have. We have k equals 1 to 6, 1/6 f of 1/6 to the k. Times k. There's what we have for this original one. And dig what happens. If I put in a 1 here, I get this back. 1/6 f of 1/6. Then I increment it. I put a 2 in. 1/6 f of 1/6 times 2. See? I get this one. So this is just more general. Okay? Now, what we want to do is we want to think, okay, we want to get more specific here. For our particular problem, we were dealing with f of x equals x squared. So look at this. Here's what we have. Our particular problem goes like this. Our particular problem, we have k equals 1 to n, 1 over n, and instead of f of 1 over n k squared, let's just do 1 over n k, f of 1 over n k. We'll do 1 over n k squared because f of x is equal to x squared. Okay, so here's what we have. So I'm just generalizing it a bit. Now, look at this. I rearrange things a little bit, and we've got k equals 1 to n of 1 over n cubed k squared. See? Because this is n squared, this is n, that's n cubed. Okay? So I just kind of squared this out and rearranged things a little bit. Okay, now, realize what this is. This is a formula for calculating or approximating the area under the curve. If you give me a value, if you give me, let's say, 100 rectangles, and I want to use 100 rectangles to estimate the area under the curve, I just replace this n with 100. See? This would be 100 cubed, this would be 100 up here, and that would be how I could estimate it. Now, the more rectangles we have, the better our estimate. So what we want to do is we want to evaluate this. We want to explore this summation with a lot of rectangles, billions of them, trillions. Heck, let's let there be infinitely many rectangles. In other words, what I want to do is I want to find this limit right here. I want to take the limit as n goes to infinity of this thing. I want to take the limit as n goes to infinity. In other words, I want there to be infinitely many rectangles. Okay? That's what I want. Because I'm reasoning that if the error decreases, the more rectangles I have, then if I let the number of rectangles go to infinity, the area should completely vanish. And I should get the exact value of the area under that curve. So let's see if we can evaluate this. Now, I want to talk about something. Let's just talk about a situation like this. Let's suppose we have k equals 1 to 4 of, let's say, k squared. We'll just look at this part. Now, there's a so here's what we've got. We've got 1 squared plus 2 squared plus 3 squared plus 4 squared. That's what this is. If we go ahead and write it out. And if you go ahead and calculate that, you'd have 1 plus 4 plus 9 plus 16. See? So that's going to be, what is that going to be? There's 25, 29, 30. So I guess that's 30, right? Okay. Now there's a formula that we can use. So it was no problem for us to add this up, but there is a formula that we can use that if we have something like this, let's suppose we have k equals 1 to n of k squared. There's a summation formula that goes like this. N times n plus 1 times 2n plus 1 over 6. Okay? This is a summation formula that works for these k squareds like this. There are formulas for k to the third, just k to the first, but this is the one we're going to be dealing with here, k squared. Now, let's see how it would work for this particular one. we've got the summation k equals 1 to 4 of k squared. So let's see what this is. I put in the 4 plus 1, 2 times 4 plus 1, all over 6. Now that should equal 30 if my formula works. So let's see what happens. I've got 2 times 5. See? 2 times 5 times 9 over 6. Okay? Now, if you notice this 2, there's a 3 in the 9, and here's a 2. Those divide out, right? Let's see here. Well, here's a 2, and then this is going to be 5 times 3, right? Oh, that's only 15 though. Did I do something wrong here? Let's see here, 15. Hang on, let me. Oh no, it's 4. There's 4 there. Yeah, and the 2. So really, you have 30. Okay, I'm sorry, I wasn't thinking. I wrote that as a 2 instead of a 4. But here's 4 times 5 times 9. 4 times 5 times 9, and this all simplifies to 30. Okay. So that's how that formula works. Now let's go back and get this thing. We have k goes from 1 to n, 1 over n cubed k squared. Okay? This is what we were working with earlier. Now this is going to equal n times n plus 1, 2n plus 1, over 6 times 1 over n cubed, right? See, I've got the 1 over n cubed I put on the n. So this is what we just looked at. This is the k squared, 1 over n cubed. Now remember, this is a formula. This is a formula for n rectangles. If we have 100 rectangles, just put 100 in for n. If we have 1,000,000, just put 1,000,000 in for n. But remember, what we're doing is we're letting n go to infinity. So now, hang on, we're about done here. And you're going to behold something truly spectacular. Okay? So we have the limit as n goes to infinity. Now, let's see what all of this is. We've got n times n plus 1, 2n plus 1, over 6n cubed. Okay? Now, think about, just to kind of cut down on the algebra. Remember from your college algebra, this is a polynomial, one polynomial over another, and we're trying to find, you can think of it as trying to find the horizontal asymptote. Or back when we did limits involving infinity. Remember, if the degree on the top and the degree on the bottom are the same, it's the ratio of the leading coefficients, right? Remember that? Now, the degree on the top you can see is 3. The leading coefficient up top is going to be 2. In other words, when I multiply all this out, I get 2n cubed and then some other terms. But what I have then is this is going to equal 2 over 6, which is 1/3. Now that right there is the limit of this Riemann sum. This Riemann sum right here. The limit is 1/3. Now, we are interpreting that to be the area under the curve. This is the limit. That is the exact area under the curve. This is the number we get when we add up all the rectangles from 0 to 1, and there's infinitely many of them. So we've got this machine, this integral right here, this integral. And we're saying, okay, make a bunch of rectangles on the interval from 0 to 1. And when I say bunch, I mean an infinitely many of them. add up all those little rectangles, all those thin little rectangles, infinitely smaller rectangles. And when you add up all of those rectangles, you get this 1/3. This right here and this right here and this are the same. In other words, this limit is that. This is the way, this right here is the way we can write that. So this is called a definite integral. And the definite integral is defined to be the limit of the Riemann sums. Think of an integral as a very powerful adding machine. It adds up infinitely many things. And notice, just like we define the derivative to be the limit of the difference quotient, we're defining the integral, the definite integral, to be the limit of the Riemann sum, the limit of a Riemann sum. So the foundation of our derivative, all the talk that we did with derivatives was a limit. The foundation of all that we're discussing with these integrals right here is a limit.